So now I'll continue the lecture and you will see. So we have proved, what did we prove so far? We have proved 1 and 2 in the Sylow theorems. And if still anybody has a doubt, they can raise it. 1 and 2, that was in the earlier lecture. So 1 and let me open that also for the sake of completeness. So that is 12. So that is this. This is what 1 and 2 we have proved, and third we want to prove. And you see in 1 and 2 also we have used only group action and nothing else. All right, now let us go to third one. I want to prove the number of Sylow subgroups of a finite group G, P Sylow subgroups that divide that Q. Q is the remaining part in the order. All right, so let me write the proof here. And after that, I will give some examples, and then I will also give you another proof. All right, so this is the 3 in Sylow theorems, part 3 or third Sylow theorems. So what do we want to prove? We want to prove. So write down what do you want to prove? To prove number of P Sylow subgroups in G, divide that Q. And what is Q? That is order of G is, we have called it N, and this N is P power, what did I call it? Whatever, P power alpha times Q, where alpha is actually VP of N, which is alpha, which is strictly bigger than 0, and Q is co-prime to P. That is GCD of Q and P is 1. P is the prime number. That is what we have. All right, now we can use 1. That's what I said. We can use theorem 1, existence of Sylow subgroups. So start with that H. Let H be a Sylow subgroup, be a P Sylow subgroup. In G. That definitely we know exists by 1. And then I'm going to consider the operation of G on P power set of G of subsets of cardinality P power alpha. Order of H is also P power alpha because it is a Sylow subgroup. And which operation I consider? Conjugation operation. That means G, any X goes to Gx G inverse, where X is a subset of cardinality P power alpha. The earlier proof 1, that was not conjugation operation, but it was a left multiplication operation. So I consider this operation. And now what are the orbits? So H is also an element here. H is also a subset here. So what is the orbit of H? That is precisely all these conjugates. G varies in G. So this is a conjugacy class of the subgroup H. And this conjugacy class by Sylow theorem 2, by Sylow theorem part 2, if H prime is another p-Sylow subgroup, then that H prime will also belong to that orbit, because we know that H prime is conjugate to H by 2. 2 or 1? Let me just check if I want to.
So it's 2.
It's 2. Okay, fine. Thank you. So the orbit, so this orbit is precisely all p-Sylow subgroups. In G. And therefore the number of p-Sylow subgroups is precisely the cardinality of this orbit. So the number of p-Sylow subgroups in G precisely the cardinality of the orbit of H under, of course, conjugacy action. And we know orbit stabilizer theorem tells you cardinality of the orbit equal to index of the stabilizer. So what is the stabilizer? So we have to find what is the stabilizer. Stabilizer of H is what? The one which stabilizes. So this is all the G's in G such that G, H, G inverse equal to H. This is the stabilizer. It's a subgroup, and this subgroup, you know, this is subgroup is we have noted the notation for this subgroup NGH. And what do you know? These are definitely contains H. That is obvious here also. G equal to identity, it contains H, or H is G equal to any small h, then this is clear. So it contains H, and in fact this is the biggest subgroup of G where H is normal. That also we know. But anyway, we don't need that. So now, therefore, what is the index? What is the relation between index of Ng and index of H? So this is a subgroup here. So this is a smaller subgroup, so index should be bigger. This is a bigger subgroup, so this index is smaller. Not only that, this is a sub, so therefore this should divide that. Agreed? So this index is Q because H has order P power alpha. And what was our problem? The number of, so orbit has cardinality, number of p-Sylow subgroups. These orbit equal to index of the stabilizer, which is this, and this divides Q. We are done. So that's finished. So the proof is finished here. 1 minute pause. 1 minute. What do you say? To ask you a question. To ask me the questions. Have any difficulty? Any difficulty? Any difficulty? Don't hesitate, I say. If you want to learn, you will have to ask difficulties. Can I go on? Are you there?
Yes, sir.
You are the only one who is talking. Rahul.
Yes, sir.
You have any difficulty?
No, sir. I understood.
Who else can I ask? I ask only those people who have shown interest to reply. Iti?
Yes, sir.
Is it clear?
Yes, sir. Yes.
All right. So let me continue. Now little example. Examples first. And these theorems are so very important. Where are they important? Where are they used? You will see their use also in the assignment, of course. but they are basically used to classify for the classification purpose. So this was very landmark theorem, and this is very, very important. You will see the use in not only in the classification but other places also. So before I go on, I want to write a small, I want to test you small exercise. All right, now suppose I have a ring A, R. R is a ring. Everybody know what a ring is, right? And for us, ring means always commutative with identity. When one say identity in the ring, that means multiplicative identity, and that we are denoting by 1. When confusion arises, one writes 1R. And then I consider the set of all invertible elements with respect to the ring, with respect to the multiplication in the ring. So that is R cross. My notation for that is R cross. This is the set of all invertible elements in R, of course, with respect to multiplication. Because we don't need to study invertible elements in with respect to addition, because everybody is invertible with respect to addition. It's an abelian group. So that is not very interesting. And why notation R cross? So various books have various notation, but this is my notation. Some will say UR and so on. So this is the nearest. All right. So this is a group under multiplication. And this group acts very naturally on R. And often it is a problem to understand this group. If you understand this group, then the understanding of ring is better. And the problem comes when this group is smaller. For example, if I take R equal to Z, ring of integers, what is Z cross? Can somebody tell me what is Z cross? Tithi. Hello, Tithi.
Yes, sir.
What is Z cross? How many elements?
So may I answer?
Sir, 1.
Only one?
1 minus 1.
Very good. It has only 2 elements. So what does it mean? That means whenever you want to say in the equation, whenever you want to cancel somebody, cancelling means you are multiplying by the multiplicative inverse. See, suppose you have a relation like this, ax plus blah 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 blah, linear equations in so many variables equal to say C. And then I want to use a Gaussian elimination type of process, so I have to make it one here and kill other elements and so on. So that means I want to multiply this equation by A inverse. And then I will use this equation to eliminate X in the other equations. This is the normal process you would have seen in the field case. But this I cannot apply other than A equal to 1 or minus 1. That is one of the reasons why studying Diophantine equations, the linear Diophantine equations, and finding their solution space is more difficult. So, because the units are only 2, 1 and minus 1, so you cannot get rid of the coefficients. You cannot make polynomials to be monic, for example. If the coefficients are not 1 or minus 1, if 1 it's already monic, if minus 1 you can multiply by again minus 1 to make it monic. So the hands are tied if the unit group is small. On the other hand, if the unit group is the biggest possible, so if K is a field, then the unit group is the biggest possible, that is K minus 0. So it's biggest possible. So then there is a comfort, you can do it easily. That is the reason Why? It's important to know what a unit group is, how big it is, and so on. And for your information again, when you are studying, for example, algebraic extension, and suppose you have a number field K over Q. This is a number field means this is the finite extension of Q. So finite extension. These are called number fields. Then finding, and you take the integers here, and this is for those who have little exposure to something what I say. If you don't have exposure, you can ignore these remarks. And then you take the integral closure here. That is usually denoted by either by Z bar, or number theory guys will also denote this by OK. This is a ring of integers in K. So this kind of diagram, and then one wants to find out what is OK cross. This is a ring, and one wants to find out what are the units there. And this is not an easy affair, even for quadratic extensions. Even when the extension has degree 2, this is not easy. All right, so that was just to tell you the unit group is very important in the study of many various fields of mathematics. All right. So now what do I say? The unit group operates. This group operates on R by multiplication in the ring. So what is the operation? R cross R to R. What is the map? Very natural map. It suggests multiplication. So any U comma A goes to UA. This is clearly an operation map. It satisfies 1 and 2 of the operation. Now, for example, you can take your ring to be Z mod N. Then you know this group, Z mod N cross. What is this? Can somebody tell me?
So is it unitary group?
Sorry?
Unitary group, UN.
What is that? You are using a different name, but I don't know what is the definition of that.
So every element has GCD 1 with N.
Very good.
And
That's
A
correct.
is
That is correct. So this is what Sonakshi says is these are all those U in, let me call it, in all those U in Z such that 1 less equal to U less equal to N or N minus 1 and GCD of U and N is 1. Is that what you meant? Sonakshi, is it correct?
yes, sir.
All right. So this is that group. And we know this Z mod N cross operates on Z mod N. And what I want you to do, this you should do it when you have a khali time, not doing anything, and then they say, what is that? Let me think. So what is the class equation? That is what I wanted to ask. This class equation is a famous, very famous equation that you would have come across in maybe somewhere in some context or somewhere you would have come across. So think about it. All right, so let us continue with more examples. All right, so let us, so the example 1. I just want to explain what we have been doing for Sylow theorems in some particular examples and give you another proof by using examples. All right, so I'm taking G equal to Z mod N. And I want to write down the Sylow subgroup. This is an abelian group, of course. So any two subgroups are conjugates. And therefore, there is only for each P, there is only one Sylow subgroup. So, and then N you have written it as P power alpha Q. Then I say then, what is the P Sylow subgroup there? It should again be cyclic because this G is cyclic, so any subgroup is cyclic. So it should again be cyclic. So that should be of what? That should be this subgroup, nothing else. Z mod P power alpha. And you see G is here, Z mod N. And how, if I write this notation, how they are related? They are related that this cross Z mod Q, this is isomorphism. And this is a canonical isomorphism. This, I will not check this. I will just write here check. You understood this map now? I have taken Z mod P power alpha and I have taken Z mod Q and take their product group. On the other hand, I have taken G and I say there is a natural map. What is the natural map there? What is the map? Can somebody tell me what is the natural map? From Z mod N to Z mod P power alpha, is there a natural map?
N goes to N mod P power alpha.
Yes, very good. So this is any A going to A mod P power alpha, comma A mod Q. That is the map. And I say this map is injective and this map is surjective also. It's a group homomorphism. All right, so that is what the beginning. This is how you, when you introduce to the groups, you deal with such things. Lots of such things you deal with. All right, so the next example. Next example, I will mix now with linear algebra. So now K is my FQ. This is a field with Q elements. And you know, if such a field exists, then this Q has to be the power of prime number. So P is prime. And also you know that the multiplicative group of such a field, of course it's a group. This is a, because it's a field, it is a Q minus 0. And this group has a nice structure. This group is cyclic. That needs a proof. And I hope you know the proof. If you don't know the proof, please do it. It is very, very interesting proof and very, very important proof. So probably you might have done for Q equal to P. Z mod P cross is cyclic. That is obvious. You know how many elements are of order P there. Anyway, so that you do it. And I am going to consider now vector space of dimension n over k. So V is vector space, FQ vector space of dimension n. And I am going to consider the group G, which is GLV. That is, I am going to consider the group, automorphism group of V over FQ. Strictly speaking, I should write here also FQ. And in the assignment, Which assignment? 3. You will be asked to compute the cardinality of this. So what is the cardinality of G? This is also finite group, and I'll write down the cardinality of G. I will show you. I have written that in exercise 3. Is it 3? Yes, it is 3. Here, this is 3.1a. Can you read it? Sonakshi, can you read it?
Yes, sir.
The cardinality, the order of the automorphism group of n-dimensional vector space K is FQ. It is this. So let me copy it from there and tell you what is it. This is Q power n minus 1 choose 2 times the product I is from 1 to n q power I minus 1. So again I will show you. You see here, this index is n minus 1 choose 2. And these are q minus 1, q power n minus 1, decrease the power and so on, go up to q minus 1. That is precisely whatever it is. So this is the order. So this is by exercise 3.5a. So I know the group order. It's a finite group of this order. Now what is the alpha? What is P VP of order of G? What is the highest power of P that divides this expression? Q is power of P. So all these guys are co-prime to P. This product is co-prime to P. Each one of them is co-prime to P, therefore product is co-prime to P. And this one is exactly P divide this. But P is Q is P power E. So therefore VP is what we call it alpha. That is E times choose n minus 1 choose 2. Agree? I want to find out that because I want to explain you what is the Sylow subgroup in this case. I don't have to write. I will just why this detailed information instead of this. I'll keep writing that only. This is the power of P. So no, alpha is not that. What I meant is, it's okay. Alpha is not that, but if I call this order to be n, I am not called anywhere, then n equal to q power n minus 1 choose 2. And now, unfortunately, I use the same q. What is there? That I will call now some other letter. Or what should I call it? M. Where now P doesn't divide M. And I want to show you there is a subgroup. You can actually write down the subgroup of order q power n minus 1 choose 2. One Sylow subgroup. And once you know one, you know all of them. They are conjugates. And conjugates are what elements here? They are precisely the conjugation. You take automorphism and conjugate it on conjugate by another automorphism. That is the all other. All right. So what is that group H? So I want to describe H. So consider H, which is that group as I will give you the name for that group because it will keep coming and coming. Maybe you also know the name of this. So it is UT N FQ. What is this group? This is the set of all. Now I will write it the matrices because it is convenient to count them then. Ultimately, I want to find the order of H. So if I write in the form of matrices, it will be easier to count. So set of all upper triangular matrices and also normalize. That is what normalize means, with all diagonal entries 1.
Hello, sir.
Yes.
Sir, I did not get how do you get VP of cardinality G equals to E into N? Choose that part.
All right. What is VP? You know, it is the highest power of P that divides the order.
Yes.
Now, as I said, this product here, that is all co-prime to P. Because that P divides Q.
Yes, sir.
See, these are all co-prime. So I only have to look at this. But that is the power of Q is the power of P. What power of P? That is Q is P power E. So this integer is nothing but P power E times this.
Okay, okay, sir. I got it.
So that is it. Who are that?
Sir, Anuj, sir.
Anuj. Okay. Fine. Anuj, you are from Pune University?
Yes, sir.
Okay, very good. So this is now I consider the H, which are upper triangular matrices with diagonal entries 1. So the elements will look like this. Matrices, square matrices of order n, and 1, 1, 1 here, zeros here, and stars here. So what is the order of H? Can you read it now? That will be one possibility here. Then there are 2 here. Then there are 3 there. Then there are 4 above. Then ultimately the top row will be n minus 1. So the number of possibilities for star is varying in the field. So this star will have how much possibility? I am computing what power of Q it is. So this will be power of Q only. And how many possibilities? What will be the power, which power of Q? So that is 1 from here, 2 from there, etc., up to n minus 1. So this is same thing as Q power n minus 1 choose 2. Is it clear what I said? See,
Yes,
how many
sir.
possibilities for this star? There are Q possibilities. Because the field has Q element. So I can put any element in the field here. The earlier row, there are 2 elements I want, and both of them I want from the field of Q. So how many possibilities? Q square possibilities, and so on. So I have to sum the power of Q. So this is the. So that shows that this H is indeed H is a p-Sylow subgroup of G. Is it clear? If something is not clear, please raise your query now, because I want to use this. Hello, Didi, is it clear?
Yes, sir, it is clear.
Very good. All right. Now, what do you? I want to give you another proof. Another proof of Sylow theorem. Okay. Let me open up my page so that I don't mess up. So one more observation, very important observation I want to make. This is called a descent argument. Descent. What does that mean? What do I mean by this argument? That means if I know a theorem for a bigger group, then I want to deduce for a smaller group. I will write it precisely. So suppose I know some bigger group G, some group G, and Sylow theorems exist for that group G, and if H is a subgroup, then Sylow theorem for H will also exist. This is a decent argument. All right. So this is the theorem I want to write. We will write it precisely and prove it precisely. You will see proof is nothing. So let G be a group, finite group. And H is a subgroup. Subgroup. And let suppose S is a p-Sylow subgroup of G. Then I want to produce a p-Sylow subgroup of H. See here. Now I have a knowledge about G, that Sylow subgroup in G exists, and I picked up that S. Now I want to use this S to produce a Sylow subgroup in H. Then there exists G in G such that H intersection G S G inverse is a p-Sylow subgroup. Of H. So you see, this proposition allows us to use the descent to go to smaller group. So if I given a group, finite group, what I will do it after this proof? What I will do is, given any finite group, I will enlarge the group so that that group will have a Sylow subgroup I know, and then I will come down. That is the idea. So that will give us another proof. All right, so let us first prove this. So proof. I am given S is Sylow subgroup, so I am going to consider, and obviously the group action I will use it. So consider the set X equal to G mod S. These are the left cosets of S in G. I'm not saying it is a group. I'm only looking at this as a subgroup. And I want to use a group action on this that we have been studying so much. Right? So how does G operates on this? By multiplication. So G operates. That is what we have been often using, this operation of G on this left coset set. Operates on X mod S by X, not X mod S, X. Remember, X is G by S by left multiplication. So that is the operation is G cross X to X. G comma X going to Gx. Not G comma X, G comma. Okay, G, this is okay here. What I meant was G comma small x map to Gx. And X here is a coset. X belongs to G by S. So just that is the operation. And now H is a subgroup. So I will restrict this operation to H. What does that mean? That means I have H cross S here. And this is a subset of this. So I will consider this composite map. And that's also operation map. That means it satisfies 1 and 2 of the operation map. Therefore, H operates on X by left multiplication. And all that I am going to study is, whenever you have a group action, ask what are the stabilizers, ask what are the orbits, what are their cardinalities, and so on. That is the only tool we have been using it so far, and that is so powerful tool. And you have seen that this comes in other subjects too. In fact, this group action comes in every subject. You will be surprised. Even differential equations have these group actions. Even the dynamical systems has group operations, and so on. All right. So the question I am asking is stabilizer of X. At X. H stabilizer. I am taking the operation on X by H. So that we are denoting X, H suffix X. And remember, X is a coset, left coset. We will use it when time comes. And what is this? I claim that this is equal to H intersection, the conjugate subgroup of S. And how to get hold of the G? This X is where? X is in X. So this X is GH, that G. Understood the statement? We will check. Don't worry. First you understand a statement, we will check that. This is for some G. G in G. You know, this G is not uniquely determined. Two cosets can be equal. Without G being equal, no? GH can be equal to G prime H. So that is why I wrote for some. As I said earlier also, this course, not only with all the AFS and all the schools arranged by NCM, I taught in many courses, and one of the motto is also teach people how to write mathematics. So that is also part of our motto. All right. So let us check that. So what does one mean by stabilizer? So let us start with an element here, and I will show you it is here, and that element is, I will show if and only if statement. So start with an H here, H in Hx. That is if and only if. H times X equal to X. Correct? That is the meaning of stabilizer. But X, I know it is GH for some. So this is if and only if HGX GH equal to GH. But that is if and only if H belong to GH G inverse. But H is already in H because we are looking at the stabilizer at of this group action H. So this is already in the intersection H.
Hello, sir.
Yes, please.
Is it,
Is it H or S?
Yes.
Which step can you point out? Here you have a problem.
No, you're writing that X is equal to GH. It is G dot S, I think.
Yes.
Where?
Coset.
Coset.
yes.
This is a coset, no?
Yes, but
X
of
is
S.
also coset.
Coset of yes.
These are the cosets of S, right?
Yes. Oh, yes, sorry.
Yeah.
This is not H. This is S. Sorry. Thank you for pointing out. This is S. This is S. And now here I have to correct it. Here it is not H, but S. Agreed? And if at all there is a difficulty, it might be this if and only if. But that you are already, you know how to do this. You see, you multiply this by G inverse, and that means G inverse H times G belong to capital S, and that means H belong to that. So do you agree to this if and only if statement?
Yes, sir.
Yes, sir.
Did we not prove then this equality? This one? I proved h is small h is on the left side if and only if it is on the right side.
Yes, sir.
So we proved that claim about the stabilizer at h at x. If you want, you write here h stabilizer so that you remember which group is acting. All right. So stabilizer we found out. And now let us look at what is x, the cardinality of x first of all. The group is operating on the set x, and what is the cardinality of x? What is x? So cardinality of x is the index of the Sylow subgroup. And this index is that remaining part. This index is not divisible by p. So p doesn't divide this. Because you have taken the maximum p power subgroup of G, that is precisely the P Sylow subgroup we have taken. So P cannot divide the index of that Sylow subgroup. That we know definitely. So here if you want to write explanation, write here, since S is P Sylow subgroup. Of G. All right. So we have proved that so what does that mean? This cardinality of the set is not divisible by P. So if you take orbits, there will be at least one orbit where P cannot divide the cardinality of the orbit. Agree? So I will write the statement. If you don't agree, you tell me. So also note that there exists H orbit. So how do orbits denote? We are denoting by X times H. These are the orbits. And remember, this X is an element in X. That means it is a coset. There exists H orbit Hx of this operation such that P cannot divide cardinality of that object. Because if every orbit cardinality is divisible by P, then the sum will also divisible by the cardinality. But that sum of the cardinalities of the orbits is precisely the cardinality of X by class equation. And then cardinality will be divisible by P. So I will write the explanation in the bracket. Otherwise, P will divide cardinality X because this is sum of cardinalities of orbits. So there exists one orbit at least, so that the cardinality of that orbit is not divisible by P. And what is the cardinality of that orbit? This cardinality I know by orbit stabilizer theorem. The cardinality of the orbit equal to index of the stabilizer. So this cardinality is nothing but the index of H, X in H. This is orbit stabilizer. Agreed? But I know this index because I know the subgroup. The subgroup is precisely this. So this is precisely what we proved is index of H, index of this subgroup, H intersection GS G inverse. This is that index. and P doesn't divide this. But P divide this. P divide the order of the stabilizer. Isn't that clear? Because this stabilizer, note, P divides cardinality of the stabilizer. Because this cardinality is precisely this HX is precisely this intersection. So it's intersection of two groups, two subgroups. And therefore that cardinality will be divisor of both of them. Because it's a subgroup in both. But this is P power, highest power P. So therefore P divides this. Definitely. And P doesn't divide this. So doesn't that mean that this guy is the highest power? This cardinality of this is the highest power of P that divides order of H. So therefore, I will write directly Hx, which is equal to H intersection G inverse is a P Sylow subgroup of H. Stop. Then we have proved what we wanted. I produce actually a P Sylow subgroup in H by assuming there is a P Sylow subgroup in the bigger group. Now anybody has difficulty, still ask me. This is very important.
So Hx is equals to H intersection GS G inverse.
Yes, very good. That we proved.
No, sir.
Therefore,
Instead of H, you have to write S.
oh, sorry. Thank you. Sonakshi, it was no. Now is it clear why this is a P Sylow subgroup?
Yes, sir.
You have to note that P divides the order of this group Hx. That we know. That is how we have chosen. The orbit is not divisible by P, but the product which is H, order of H, which is divisible by P, and therefore this is divisible by P, and this P, this is the order of this Hx, will divide both these. Order of H as well as order of G inverse, because it is a subgroup of both. Therefore, the only we have to note that P divide this. So Hx will be, order of Hx will be divisible by P2. Therefore, it is what may happen that if you start with a subgroup G, which order is co-prime to that P, then of course this intersection will be empty, not empty, identity only. So then the P Sylow subgroup in that H will be trivial, but it's built in this everything. See, you should also look at the extreme cases. Like I've heard Nitin many times is applying the argument to empty set. See, these are extreme arguments, but they give you the clues. All right, now can I assume that everybody understood this theorem? This is called a descent theorem. That is because you deduce a consequence from a bigger group to smaller group. So this proves a Sylow theorem 1, another group. All right, now I want to use this. I want to give you such a situation. All right, so I want to give, so now go back. So original problem we started with was G, any group, any finite group G. Finite of order n, and n is P power alpha times, I call it Q, but now let us switch to M because I want to use that Q for something else, and P doesn't divide M. And I want to prove that P Sylow subgroup exist in G. This is what I want to do. Rather, I want to deduce this. This is the first Sylow theorem. Then number, etc. That is, as you saw, that is much easier. The real energy went in proving Sylow theorem 1. All right, now if I want to use this argument, that means I should enlarge this given group G to a bigger group where the Sylow theorem is obvious. Right? So now I will say consider. What can I consider? Consider Q equal to P power alpha. And the bigger group I want to consider is U, P, N, F. So first of all, you have to note here, what did I use? Can somebody raise it? What do I use here? Note that FQ exists. That means given any power of a prime number, I can always construct a field who has precisely Q elements. This needs some proof. Does anybody have any idea how does one prove existence of such a field? For Q alpha equal to 1, it is obvious. Then you can take that field to be Z mod P. Whom can I ask?
So we can use the theorem that if R is a commutative ring with unity and
Yes.
M is a maximal ideal, then R quotient M is a field. For that,
But
R
for which ring will you use?
is a ring of polynomial Rx
Yes.
and any polynomial of degree. Suppose we want to construct P to the power alpha, so we will
Yes.
consider the polynomial of degree alpha.
Polynomial of degree alpha, or what is it to do with P? So what is the ring you are considering, Sonakshi? You are correct. But
No. So, we can consider the ring ZP, Z modulo
Z
P
modulo.
Px, yeah, ring of polynomial within
Yes.
entries from ZP,
Yes.
and
And
then
then
consider a polynomial of degree alpha in this ring.
degree alpha. Okay. So capital F and F is a polynomial degree of F equal to alpha. That is what you are saying.
Yes, sir.
Yes. Then
Then sir, ZPX is PID,
yes.
and any irreducible polynomial in a PID is that generates a maximal ideal.
But you didn't say F is irreducible or not.
Yeah, F has to be irreducible polynomial.
So F irreducible over Z mod P and degree is alpha.
Yes, sir.
Then if you look at this field, this is a field because it's a PID irreducible polynomial generate prime ideal, and PID non-zero prime ideals are maximal. Therefore, this is a field. But how do you know such a polynomial exists? How do you know that in polynomial ring Z mod Px, there is a polynomial which is irreducible and of degree alpha? And alpha, you have no control. Alpha can be anything, no? So that means you will have to prove a statement. If you take a polynomial ring over a finite field Z mod P, then for given any natural number alpha, there is a polynomial of degree alpha which is irreducible. Do you
Sir?
need to prove? Do you need to prove this or not?
Yes, sir.
You need to prove this. See, I'm not worried about the proof first. I'm worried about the statements and what we need to. When you say take this, when you say take this means you have to have some evidence that such polynomials exist. No? Yes. What do you say for that?
So we can take the polynomial x to the power p to the power alpha minus 1 and consider its splitting field.
You are taking the polynomial what? X to the power p to the power alpha
Alpha minus 1.
minus 1 and then
And then considering its splitting field, we can prove the existence of that field.
you take the splitting field. Then, but now you are not taking Z mod P. Now, Titi, you are doing something else.
Okay, sir. Okay.
See, you should also, having understood the problem, you should target to the problem. If you start mixing up some other thing, then that means you are not focusing. All right, anybody has any idea? How do you prove this?
So we consider the polynomial x raised to p raised to alpha minus x in the field of
Minus what?
minus x.
X to the power p to the power alpha minus x. This you are considering. And then?
Yes. And the roots of this polynomial are nothing but the field fq. The non-zero roots are the field fq cross. That is the elementary construction we do to construct the field fq.
So that means you are not taking the ring to be Z mod P. That's what you are saying.
Yes, sir. The
So which field are you taking?
ZP, sir.
No, I am not. I am confused. You are saying consider these polynomials and then do what? What? You have considered these polynomials. This polynomial is Z mod P X, that I agree. And then what? Then what do you want to do from there? That is not clear.
So we just connect.
Maybe something is clear in your mind, something, but you are not expressing. So try to do that. Try to do that. And then you will succeed. But anyway, so I don't want to spend much time on that. If we want to do this, we can discuss more in the exercises. So this problem has to be addressed sometime. So I'll just mark it. So I know there is a field with q elements for any power of p, and then I consider this group ut and fq. And what is the order of this group ut and fq? That also we know. The order of this group ut and fq is we know. We have just computed in that example, no? It is q power. Here is the order. Q power n minus 1 choose 2. That is the order. In fact, it is a p group. This is a p group. Of order q power that. All right, we got hold of the group this, and I want to now put. So this is a subgroup of GLN. So UTN FQ. This is a subgroup of GLN FQ. and somehow I want to embed the given group in this. So what am I looking for? Let us write. We are looking for G inside this. This map we are looking for. That is, we are looking for a group homomorphism from G to this, and it should be injected. If we manage to do that, we are done, because then I can use the descent argument. I know, not here. Actually, I should know, this I written wrongly. I should embed the group G inside this. G inside the GLNF. Injective group homomorphism. If I can manage, then I know this group has this Sylow subgroup. And therefore, I will conclude G as the Sylow subgroup by the descent argument. Here, this is the descent argument. If I know one subgroup of a bigger group, which is Sylow subgroup, and I intersect with suitable conjugate of that Sylow subgroup with H, and that will become a Sylow subgroup in G. Is it clear what is our requirement now? Our requirement is to put the G inside the GLNFQ. All right? Is it clear, this argument? And then we are done. Please. If it is not clear, I want everybody to understand here only. 99% argument should be understood here only. Hello, Soham.
Sir, can you please repeat this?
I will repeat it, but I want to talk to Soham first. Soham, are you there? All right. He doesn't respond, so maybe he doesn't want to learn.
Yes, sir.
All right.
Yes, sir.
Yes, please. Soham, is the argument clear to you?
Yes, sir. Yes, sir.
Can you explain, please, to Sonakshi is asking some difficulty. Sonakshi, raise your difficulty.
Sir, I didn't got the idea. I know the descent theorem that you are going to use,
So
but
you
the
can
idea.
repeat also. So can you
Soham,
repeat that?
can you tell her the idea?
No, not that part, sir. No, this part is not clear, sir.
All right. So, Sonakshi, if I could manage to give you an injective group homomorphism from the given group G that we started with inside GLNFQ, suppose,
Yes, sir.
then can I not conclude from this? This I know this is a p-Sylow subgroup of the GLNFQ that we have checked in example.
Yes, sir.
So when I suitable take the conjugate and intersect with the G, won't it be Sylow subgroup? That is what
Yes,
the
sir.
descent argument is.
Yes, sir. That will be.
And then that will do. That will finish our problem for the existence of a p-Sylow subgroup in G.
Okay, sir.
So therefore, we have to prove that G can be embedded in a GLNFQ.
Yes, sir. I
And
got
G
it.
is a finite group. G is a finite group of this order, p power alpha times q, and p is that, and that is how we have chosen our field, which has cardinality p power alpha, and that is how we have come to UTN, because this n is this n. All right, and then we have counted everything, and then we want to put G inside that GLN.
Yes, sir.
All right. All right, now it becomes a linear algebra. All right, so consider, I'm trying to give an injective homomorphism. So consider, so GLN FQ is an n-dimensional vector space over FQ, and I want to look at the automorphisms, isn't it? So note that, so consider n-dimensional FQ vector space V. This is GLV, GLNV. GLV FQ. This is the coordinate description of this group. Okay, and what are the automorphisms of V then? That is precisely the elements of GLA. Now, how do we describe automorphisms of a vector space? How does it describe the odd group? Odd VFQ. We know this is nothing but GLN FQ. This is the group we are interested in. This is the group we are interested in. So what are the elements here? They are automorphisms. F, V to V, K automorphisms. How do you produce automorphisms of a vector space? How do you produce?
So by mapping basis element to the basis element of.
Very good. Very, very good. That is the first theorem you ever learn in the linear algebra. So start with the basis. So let V1 to Vm in V be the K basis of V. K is FQ. So everywhere K is FQ. FQ. So I am defining a map from define.
Hello, sir. There is a tutorial at 6 o'clock.
Oh, sorry. I'll finish. Sorry. I will 1 minute. I will finish. So I am defining a map. Why did I call it M? It is N. This is N. I am defining a map Sn to OT. What is the map? Any permutation sigma. I should give an automorphism. That means I should tell you where these basis guys go. So I will call it F sigma. F sigma from V to V. You define this by Vi going to P sigma. Sigma is a permutation. This is obviously non-automorphism because basis is mapped onto basis. They are permuted. So it is an element in the automorphism. So this is obviously a group homomorphism that you check. And I know any group I can embed in Sn. This is Cayley. G to Sn. This is a Cayley map. And that we know it is a injective group homomorphism. This is injective, and also you have to check this is injective. So that is how you have embedded in the automorphism. That is what the requirement was. This was a little faster, but we will discuss this in case of difficulties in the tutorial session next or in the next lecture. Sorry for the I got delayed.